Welcome to the walkthrough for homework number 4. In homework number 4, we're putting together two things we've done before. We've done motion in a straight line, and we've done motion up and down. And now we're putting together the two concepts into one to do projectile motion. Projectile motion is the motion a ball makes when you throw it in the air, or a golf ball when you hit it. And it's very useful to kind of be able to predict all of this. In the horizontal direction, the projectile motion, we've got a constant velocity, so our position is just that velocity times time. In the vertical direction, we have our initial velocity we launch with in the vertical direction, but gravity is bringing us down the whole time, right? So we start up, but we come back down. And let me read to that one real quick. If we launch at some angle, so I would launch here at some angle theta with some initial velocity v naught, I can calculate the x piece and the y piece of those two. And with this equation down here, I can actually tell you how far it's going to go, because our range d is v naught squared, so this squared divided by the acceleration of gravity onto the sine of twice this angle, sine of 2 theta, right? So v naught squared over g sine of 2 theta gives us the range of the object we're throwing, right? A couple of other things we're introducing here. Orbital velocity is the first. Orbital velocity is the velocity that an object going around the Earth would orbit at, or going around the Sun, or going around the Moon. So you've got a large object that has some mass m, and you're a distance r, this little r, from its center. So whenever you look at r, this is not the distance above the Earth. The satellite is. It's a distance the satellite is from the center of the Earth. And then there's this capital G. This capital G is the universal gravitational constant, and it's right here. Also, just so you have the numbers, here's the mass of the Earth, here's the mass of the Sun. You can see the Sun is much larger than the Earth. And remember, the distance r is the distance from the center. So if we're talking about orbiting around the Earth, you've got to take into account the radius of the Earth plus the height of the satellite. The other thing that's out there in this is the escape velocity. The escape velocity looks very similar to the orbital velocity, but it's the square root of 2g times the mass times your distance from the center of the object. All right, so if you are, let's say here's the Earth, all right, and there's the center of the Earth, and you're out here in a spaceship, your orbital velocity, right, is given by this distance r, gravitational constant, and the mass of the Earth. And the same thing with your escape velocity. It's this distance r. Now that distance r for escape velocity, typically we're thinking about from the surface of the Earth, how fast you have to get moving to hit escape velocity. But you can also think of it in terms of, oh, I'm in orbit, now I want to get away, how fast do I need to go? All right, so let's look at the problems. You launch a toy rocket straight up. It has initial velocity v. How high off the ground will it be after 2.435 seconds, right? So in y, right, y is our v naught. I'll just talk through this. Y is our v naught. Here's v naught. Here's t. We know g is 9.81, right? Here's our equation right here. V naught y times t minus 1/2 of g times t squared. So we just put in all the pieces, 9.81, the time we're given, the initial velocity we're given, and that gives us the height that this rocket will be at a given time, at this time, 2.435 seconds, right? Now we're hitting a ball. We're hitting it at this angle theta, 32.24 degrees. It's important to note the degrees, right? How far will it travel before it hits the ground? Well, we've got the initial velocity. We have the angle it's launched at. We go back up to the range equation. All right, the range equation says the distance it's going to go is the initial velocity squared divided by the acceleration of gravity times the sine of twice the angle. Got to remember, in this problem, the angle is given to you in degrees, so you have to set your calculator in degrees to make sure you get this right. Right? Because when you take the sine, it's going to need to know that those are degrees. Introduce a new equation with question 3, the time of flight. All right, and you can see the time of flight depends on just your initial velocity, the acceleration of gravity, and the angle you fire something off at. So here we are. What's the time of flight of a baseball? Well, we've got our initial velocity. We have the angle in degrees. So again, make sure your calculator is in degrees. Have our angle in degrees. We just plug all of these in along with the acceleration of gravity on the surface of the Earth, 9.81. We have the radius of the Earth. We have a satellite going in orbit around the Earth. And this brings up what I was talking about earlier. Right? We have the Earth, which is much rounder than this. And it has some radius of 6371 kilometers. And then above the Earth, all right, there's a satellite going in orbit around the Earth, just above the Earth, and it is at a height of 388.3 kilometers. Now, all of these we have to convert to meters in order to use them in the equation. So 6,371,000 6,371,000 meters, right? Because you just multiply it by 1,000 and go from kilometers to meters, and 388,300 meters. Now the distance we are from the center of the Earth then is just going to be the sum of these two distances, right? So we've got R, we have the mass of the Earth, we have the universal gravitational constant. You can calculate the orbital velocity using the orbital velocity equation right here. Now we're around a moon. So we're on a moon. It has a mass of 4.11 times 10 to the 12th kilos, has a radius of 1,374.12 meters. What's the escape velocity? Well, we know the mass of the moon. We know the radius of the moon. That's our distance r. We know the universal gravitational constant. So we're just going to take all of these and stick them into the equation for escape velocity and calculate the escape velocity. This problem is actually designed so when you get that, the escape velocity is low enough for this moon that most of us could jump off of it. Right? It's a very small moon. Right? 10 to the 12th. I mean, 1374 meters. That's just a little over a mile in radius. Right? So it's it's under a mile in radius. All right, so less than a mile in radius. It's a really small little moon. All right, that's it for this walkthrough. Hopefully that helps.